Similarity can suggest related entities, but it cannot enforce a path. RDFLib SPARQL follows the required relationships and returns only facts that satisfy the graph pattern. You'll run SPARQL property path queries in Python to return exact people and the witnessing graph paths for each match. I'm Professor Pi, teaching search and IR with simple Python. Linked data looks like a web of tiny facts, triples that name a subject, a predicate, and an object. The problem is practical. Keyword search or embeddings tell you what is similar, but they don't guarantee that a person actually works for an organization that is located in a specific country. SPARQL property paths let you demand that exact chain of relationships. Think of a property path as asking for a chain of handshakes. A person shook hands with an org, and that org shook hands with a country. The payoff is precision. Only matches that follow the exact chain come back. The trade-off is scale. Long or transitive paths can touch a lot of triples, so keep an eye on breadth and depth. We'll build a tiny RDFLib graph in Python. Then we'll run SPARQL queries with property paths to find people whose employers resolve to a target country. Along the way, we'll count supporting evidence, follow nested locations, and finally print explicit witness paths so every match is auditable. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we need a minimal graph that actually contains a person, an organization, and a country, connected by two triples. This snippet creates the smallest RDFLib graph that can support a multi-hop query. It builds an RDFLib graph and uses graph.add to insert two explicit triples for each connected case. The code uses URI-like nodes from EX, so we get readable labels like ADA and ACME, and the relationship names works for and located in. Keyword or vector retrieval might tell you ADA and ACME look related, but it cannot enforce that the organization has a country edge. The snippet finally prints graph size to confirm how many triples are present, which shows the linked data evidence is now available for later SPARQL traversal. With the graph in place, the next step is to ask for people who actually reach the country via two hops, not just those that look related. This example issues a SPARQL query with RDFLib graph.query and a property path that uses the slash operator to compose two predicates. The where clause asks for person, where works for, followed by located in, reaches UK, so the slash requires the sequence of edges. The graph intentionally includes bow and beta as a negative case because bow points to US, while ADA points to UK. The query result therefore binds only the person that satisfies the exact two-hop constraint, demonstrating the first payoff over ordinary lexical or embedding retrieval. Filtering for exact matches is useful, but often you want to know which targets have the most supporting evidence. The next snippet counts support per country. This code turns exact path matches into a small evidence ranking by keeping the property path in the where clause and then group by and count to summarize support per country. The query returns counts of people that satisfy the same structural predicate chain instead of a similarity score. Python sorts the rows after query execution, so the displayed winner is deterministic, which matters when you use this as a baseline for evaluation. The printed output shows which country has the most matching people and how much graph evidence supports that choice. Linked data can nest places inside places. To find people whose orgs point to a city which points to a country, we need transitive hops rather than a fixed two-step path. This snippet lets RDFLib follow nested location links using the SPARQL property path operator located in plus. The plus means one or more located in hops. So an organization that points to lab, which points to London, which points to UK, will still match. The code shows that array can match through intermediate nodes without changing the entity selection logic. Increasing transitive reach recovers more valid matches when real graphs place locations in multiple layers. But it also broadens the search space and can slow queries on larger graphs. Counting and transitive reach are helpful, but analysts often need auditable examples. The final snippet binds the intermediate nodes so we can display the exact path that proves a match. This example combines RDFLib property path filtering with explicit variables, so each match comes with a witness path. The SPARQL query keeps the concise path constraint and then binds org and place, so the result shows the organization and any intermediate place that led to the country. Python formats rows into readable graph paths, adding the final country hop when the organization first points to a city. The output lists the number of exact bindings and shows one concrete path that witnesses a match, which mirrors the kind of baseline you inspect during error analysis. On a real project, you would map this to a larger knowledge graph like DBpedia or a company knowledge base. Replace the tiny EX nodes with real URIs and run the same queries against a SPARQL endpoint. The same audit patterns help trace why a person was selected and where the graph evidence lives. 3 quick takeaways. Property path queries enforce structure, not just similarity. Use them when you need to require specific chains of predicates across a graph. And be careful with transitive operators. They increase reach, but also the search space and query cost. For one concrete next step, run these queries against DBpedia or Wikidata and use limit plus group by to manage result volume while you observe how property path reach affects performance. If short, practical IR helps, subscribe and watch the IR videos.